In this video, we're going to look at another example of separable differential equations. This is going to be a word problem. All right, so we have a beverage containing 6% alcohol by volume and another beverage containing 4% alcohol are both pumped into a vat which initially contains 1,000 liters of beer at 3% alcohol by volume. The rate at which the 6% beer is pumped into the tank is 10 liters per minute, and the rate at which the 4% beer is pumped into the vat is 5 liters per minute. The resulting well-mixed solution is pumped out of the vat at a rate of 15 liters per minute. So the volume never changes because you've got a total of 15 liters per minute of beer coming in, and the solution mixes, and then you have 15 liters per minute of solution that leaves the tank. The question asks us to what is the percentage of alcohol in the tank after 60 minutes. It also asks us to find what is the percentage of alcohol in the tank as time grows to infinity. All right, let's do that. So what we have is, let's label y of t is equal to the volume in liters of pure alcohol at time t. Pure alcohol. Now let's look at dy dt, rate of change of y with respect to time. So the units would be liters per minute. This is going to be rate in minus the rate out. Now, what is the rate of alcohol that's coming into the tank? Well, we have a 6% solution that's coming in at the rate of 10 liters per minute. That's going to be 0.06 times 10. We also have another solution that's coming in, another beverage is coming in with a concentration of 4% alcohol at a rate of 5 liters per minute. That's going to be plus 0.04 times 5. Now, what is the amount of alcohol that's leaving the tank? Well, if we take the concentration of alcohol, which is y of t, divided by 1,000, this is the concentration of alcohol at time t, multiplied by the amount of solution that's leaving, we get the liters per minute of pure alcohol leaving the tank. So let's label these. So all of this is rate in, this is liters per minute of pure alcohol entering the tank. Entering the tank. This part is the liters per minute of pure alcohol exiting the tank. Pure alcohol exiting the tank. Rate in minus rate out. All right, so the differential equation becomes dy dt. If we simplify this, we're going to get 0.06 times 10, that's 0.6, plus 0.2, that gives us 0.8, minus 15 divided by 1,000, that's 0.015, 0.015 y. Now let's separate the variables and solve this differential equation. So separating the variables, we get dy divided by 0.8 minus 0.015y is equal to dt over 1. So we have separated the variables. Now we just have to integrate both sides and solve for y as a function of time, where y of t represents the volume in liters of pure alcohol at time t. All right, so we have integral 1 over 0.8 minus 0.015y dy is equal to integral 1 dt. We integrate both sides. We're going to apply U substitution. We will let U be equal to 0.8 minus 0.015y. Differentiate both sides, and we get du is equal to minus 0.015 dy. So let's label this as U substitution. So we have integral of 1 over u du. So this integral is going to be ln of 0.8 minus 0.015y divided by negative 0.015. This negative 0.015 comes from the fact that dy is equal to du divided by minus 0.015. And on the right-hand side, we get t plus c. Now let's cross-multiply so we can isolate the log function. So we have log of 0.8 minus 0.015y is equal to minus 0.015t minus 0.015c. Now exponentiate both sides so we can get rid of the log function. So we have e to the ln of 0.8 minus 0.015y is equal to e to the power of negative 0.015t minus 0.015c. Let's put all of this in brackets. Now we can use the exponential law and simplify this, and so we get e to the minus 0.015t times e to the negative 0.015c. So e and log cancel, we get 0.8 on the left-hand side, we get 0.8 minus 0.015y, all in absolute value. This is equal to, and let's call this all this constant, let's just call it a. So a times e to the negative 0.015t. And we should write that down someplace. Let's write it down here. A is equal to e to the power of negative 0.015c. All right, so now the next step is remove the absolute value. So we get 0.8 minus 0.015y is equal to plus or minus a times e to the minus 0.015t. Of course, we're going to replace plus or minus a by another symbol, say b. All right, so we have 0.8 minus 0.015y is equal to plus or minus a, e to the minus 0.015t, and we replace plus or minus a by b. So we get b e to the negative 0.015t, where b is equal to plus or minus a. So we have 0.8 minus 0.015y is equal to b e to the minus 0.015t. Now let's solve for y. So we're going to get, actually, let's just use the initial condition and solve for the unknown constant b. What is the initial condition? Well, we have, initially, we have a 3% alcohol solution, and we have 1,000 liters of solution in the tank. So y of 0, the initial amount of alcohol, the pure alcohol in the tank, is going to be 0.03 because it's a 3% solution, multiplied by the volume of the solution, multiplied by 1,000, and we get 30 liters of pure alcohol at time t equals 0. So when time is 0, when t is 0 initially, y equals 30. We have 30 liters of pure alcohol at time 0. This enables us to solve for the constant b. So we have 0.8 minus 0.015 times y, which is 30, is equal to b times e to the negative 0.015 times 0. And if we simplify this, we're going to get, what do we get? We're going to get, let's calculate this. We're going to get b is equal to 0.35. All right, let's put this back in. So we have our expression. So we have y in terms of t. 0.8 minus 0.015y is equal to 0.35 e to the minus 0.015t. Now we want to solve for y as an explicit function of time. So let's subtract 0.8 from both sides and divide by negative 0.015. So we get negative 0.015y is equal to 0.35 e to the negative 0.015t minus 0.8, and divide both sides by negative 0.015. And if we simplify this in fractional form, we get y of t is equal to minus 70 divided by 3, that's after some simplification, e to the minus 0.015t plus 160 divided by 3. This represents liters of pure alcohol at time t in the tank. All right, so the second part of the question asks us to find the concentration of alcohol in a tank after 1 hour, after 60 minutes. So we have y of t is equal to minus 70 over 3 e to the minus 0.015t plus 160 over 3. This represents liters of pure alcohol in the vat at time t. Let's plug in t equals 60, and we obtain y of 60 is equal to minus 70 divided by 3 e to the negative 0.015 times 60 plus 160 divided by 3. If we simplify this, decimalize it, we get y of 60 is equal to, we get minus 70 over 3 e to the minus 0.9 plus 160 over 3, and let's decimalize that, put that into a calculator. We get approximately 43.85 liters of pure alcohol in the tank after 60 minutes. So that's the total amount of alcohol in the tank after 60 minutes, pure alcohol. So what is the percentage of the alcohol in the tank after 60 minutes? To find the percentage, we take the amount of pure alcohol that we have divided by the total amount of solution, which is 1,000 liters. So the percentage alcohol is simply going to be y of 60 divided by 1,000 times 100%. Now let's leave this in calculator ready form. So percentage in exact form, percent alcohol is equal to y of 60, we found it to be minus 70 divided by 3 e to the minus 0.9 plus 160 divided by 3. Its decimal representation would be 43.85 liters. Divide this by 1,000 and multiply it by 100%. If we calculate this, the percent alcohol, let's decimalize it, is equal to approximately 43.85 liters divided by 1,000 multiplied by 100%, and put this into a calculator, we get approximately 4.39%. So after 60 minutes, the concentration of alcohol is approximately 4.39% in the tank. So we found the percent alcohol in the tank after 60 minutes. Now, the second part of the question asks us to find the percent alcohol in the tank after a very long time, as t goes to infinity. So as t goes to infinity, we want to find the percentage of alcohol in the tank. How do we do that? Well, we have y of t, which represents the volume of pure alcohol in the tank at time t. Let's take the limit as time goes to infinity. Y of t is equal to minus 70 divided by 3 e to the minus 0.015t plus 160 divided by 3. Now, if we take the limit as t goes to infinity of y of t, the negative exponential is going to approach 0 because we get e to the power of minus infinity. So that's simply going to give us 160 divided by 3. So to find the limiting concentration of alcohol in the tank after a very long time, as t goes to infinity, we take the limit as t goes to infinity of y of t divided by 1,000 multiplied by 100%. So we have 160 divided by 3. That's the limit of y of t as time goes to infinity, divided by 1,000, multiplied by 100%. So as time goes to infinity, let's decimalize this, we get 5.33%. The solution becomes 5.33% alcohol. This is the concentration of alcohol in the solution after a very long time. Now the question becomes, we can answer an interesting question is, can we get the same answer, this part of the question, 5.33%, the eventual concentration of alcohol in the tank, without using any calculus, just by using basic chemistry? Let's try that. That's also interesting. And then we will basically get both answers agreeing with each other. All right, so let's now verify our answer by intuition. Let's compute a weighted average of the percent alcohol based on the two rates of alcohol entering the tank. And since the volume of the vat always remains the same, it remains at 1,000 liters because the inflow rate, so inflow rate of solution is equal to outflow rate of the solution. And that's because we have 10 liters per minute coming in from one of the beverages plus 5 liters per minute for the other beverage, and the two are mixing, and the well-mixed solution leaves the tank at rate of 15 liters per minute. So as far as the volume of the tank, it never changes. It's always going to be 1,000 liters. Of course, the concentration of alcohol in a tank is changing and is a function of time, but the volume of solution in a tank never changes because you have 15 liters per minute of solution coming in and 15 liters per minute of solution leaving the tank. So now let's do a weighted average of the percent alcohol. So percent alcohol is going to be equal to, we have 10 liters per minute coming in for the beverage that has 6% alcohol, divided by 10 plus 5, because we have a total of 15 liters that's coming in from both beverages. Multiply that by 6%, plus the other solution has is coming in at a rate of 5 liters per minute, divided by 10 plus 5, that's the total amount of solution that's entering the tank, and multiplied by the concentration of the second beverage, which is 4% alcohol. We do a weighted average. So if we do a weighted average, we get the eventual concentration of alcohol in the tank. And we get 4% from the first term, and we get 1.33% for the second term. They add up to 5.33%. Exactly the same answer as before. On page 6, there it is, 5.33%. All right, let's now look at a diagram just to review what we've done. So what we have is we started the question. Basically, we have 6%. We have a beverage that's 6% by alcohol, by volume, and that beverage is coming into the tank at rate of 10 liters per minute. The other beverage only has a concentration of 4%, and that's coming in at a rate of 5 liters per minute. So in fact, the 6% is more important, the beverage that contains 6%. Why is that? It's because there's twice as much of it coming into the tank. There's 10 liters per minute that's coming into the tank. And we kind of used that when we were doing our weighted average to find the eventual concentration of alcohol in a tank. All right, so we have dy dt is rate in minus rate out, where y of t represents the liters of pure alcohol at time t. The rate in is going to be 0.06, 6% solution, 6% alcohol in the first beverage, multiplied by 10 liters per minute, plus the other beverage has 4% alcohol multiplied by 5 liters per minute. Now the rate out is a little bit tricky. The rate out is the concentration of alcohol at time t, which is y of t, which is liters of pure alcohol at time t, divided by the amount of solution in the tank, which is 1,000 liters, multiplied by the amount of solution that's leaving, and we get the amount of pure alcohol that's leaving the tank. This is really important. So the first part, y of t over 1,000, represents the concentration of alcohol in the tank at time t. 15 liters per minute is the amount of the volume of solution that's leaving the tank. When we multiply these two quantities, the concentration multiplied by the volume of solution, we get the volume of pure alcohol that's leaving the tank. So now we have our differential equation. dy dt is rate in, which is 0.8, minus rate out, which is 0.015 y. And dy dt represents liters. The units are liters per minute of pure alcohol, the rate of change of the volume of alcohol in the tank. Now, y of 0, to find the initial volume of pure alcohol in the tank, the tank initially was at 3% alcohol by volume, so we take 1,000 liters, multiplied by 0.03, and we get 30 liters of pure alcohol at time t. And we basically have a differential equation. We apply separation of variables. We also have an initial value, y of 0 is equal to 30. We have an initial value problem that we solved by separating the variables and integrating both sides. And we got y of t, which represents the liters of pure alcohol at time t. And to find the concentration of alcohol at any point in time, we took y of t, which was liters of pure alcohol at time t, divided by the amount of solution, which is 1,000 liters, multiplied by 100%, and we got the percent alcohol in the vat at time t minutes. All right, thanks.